All right, so the last class we were discussing about the various dissipation forces. So we are still talking about the different maneuvering models, and we were discussing about how we found the rigid body mass matrix, rigid body. So let me just put it here. Yeah, so we had our rigid body mass matrix plus the added mass matrix multiplied by the velocity vectors derivative plus rigid body Coriolis matrix, added mass Coriolis matrix, plus a dissipative damping matrix, which may be linear or nonlinear, and then if there is any hydrostatic component that comes here, and that was equal to tau wind plus tau wave. So this is where we were. We were discussing the equations of motions of these. So we had originally looked at what these quantities would look like. Then later we investigated what happens to the added mass and the corresponding Coriolis matrix. And in the last class, we were discussing about these dissipative forces. Right? We understood that this dissipative matrix, DVR, is actually can be separated out into two components. One is the linear part, and then you have the non-linear part, which really depends on VR. Okay. All right. Can anybody quickly recollect what the linear part was coming from? So what was causing this linear part of the damping to come up?
Potential skin friction.
Correct. So we had this was coming due to the potential damping. And the skin friction. And what was the nonlinear part coming due to? Sorry?
Turbulent boundary layers.
Laminar boundary layer.
No, sir, turbulent boundary layer. Because of the non-linear.
Yes, it was coming from the turbulent boundary layer. What else?
Wave drift.
Wave drift also was coming into the nonlinear part, right? So those are some of the other things which was causing the so-called nonlinear damping. We looked at the idea that the linear damping matrix actually can be expressed in this manner, where we have these hydrodynamic derivatives coming into the play, and we saw that there is a good amount of coupling between the sway, roll, and yaw. So you see those cross-coupled terms are present in this system. Okay. Now, we also saw that there is some coupling between the heave and the pitch, which is expected, but we also expected to see something here as well as something here. But we can kind of consider that surge can be decoupled to the other modes in some sense, because primarily we are looking at the propulsion forces and the thrust when we are looking at the surge mode of motion. So small oscillations are not of significant to our dynamics or the problem. So therefore we can disregard them, we can comfortably neglect them. But please be aware that these terms are not necessarily zero, but their contribution will be much smaller than what you see in the diagram. So this is something that we can get away with more or less because of the symmetry of the vessel. Okay, so when we have a surface vessel, this damping matrix gets simplified a little bit, and we only have these 5 different terms which are non-zero in nature, and they can be approximated basically based on what is the zero frequency damping which is coming into the picture. Remember that typical radiation damping will be zero at zero frequency when there is no forward speed. So when the vessel has no forward speed, or means zero forward speed, in that case the radiation damping at zero frequency tends to zero. But the viscous effect damping, even at zero frequency, is not equal to zero. Okay, so here when we take this damping matrix, it actually has contributions due to both. So when I say that I'm looking at the zero frequency, it need not necessarily be zero, even though I may be looking at a zero speed application like a dynamic positioning system where my ship is not moving significantly. Still, my damping terms need not be zero. I hope that part is clear. Yes? Yes, no?
Yes, sir.
Yes. Is there a chance that I can see you all? I really liked yesterday's class. All right, excellent. This is much better. Okay, now let's proceed further. So today we'll talk about the non-viscous, the non-linear damping part, and we'll primarily focus on a couple of methodologies. So you can kind of see that today what we will do is we'll first talk about the damping, how we can apply a first principles approach to approximate those dampings. And then we'll look at what is our natural Abkowitz model, where we are not doing a first principles approach. So I'll try to tell you what is the difference between the two approaches. So in one case, we really want to model the damping through the physics in some way. In the other case, when we are looking at the Abkowitz model, we are not really modeling the physics. We are kind of doing experiments, getting the data from it, and doing some curve fitting exercise rather than actually modeling the physics. So we'll take a look at both the approaches just to keep them at the back of our mind as we progress further with talking about modeling. Okay, now when we are looking at the so-called surge force, which is coming in the surge direction when the vessel is moving forward with some speed, okay, this UR here represents the relative speed of the ship with respect to the water. So it is actually taking the relative to the current. So if there is a current, what is the relative velocity of the ship with respect to the water? That is what we are calculating. And then we are using the x component of that, and that is telling us what will be the force. So what we are doing here is half times rho, where rho is the density. S is here represents the surface area of the vessel, or the wetted surface area of the vessel. 1 plus k, where k is called as the form factor. And then we have the CF value, which is the skin friction coefficient. And then you have the U square. The skin friction coefficient is given as shown here. This is something where what we are taking is, this is the portion coming due to this frictional part, and this is the part which is coming due to the residual resistance. So this includes wave making resistance, and then you have other pressure drag and other things which come here. And this is purely skin friction.
What is this wave making
Friction.
So when you are actually moving the ship through the water, let's say calm water, you generally have a wave which gets generated, right? When you saw when we were doing the test in our wave basin also, there's a Kelvin wave pattern which gets generated, which means that basically I'm looking at if a ship is looking something like that, you'll see that there'll be a diverging wave which is moving away, and then followed by it also has transverse waves which are moving to the back. So where's my pointer here? So you see that the wave is kind of having some diverging angle here, right? So those waves which are getting generated when the body actually moves require some energy to be made, and that energy is being taken away from the system. So that also acts as a part of the so-called damping force. So that portion of these things, they do not depend on Reynolds number. We typically assume that this part depends on the Froude number, this part depends on the Reynolds number. So one part is coming due to the frictional part where the scaling is happening with respect to the Reynolds number, the other part is happening with respect to the Froude number. And we kind of talked about the idea that typically we always scale our models using Froude number. So therefore, whenever we are doing the scale down, the skin friction part will not be matched between your prototype and the model. So you have to figure out an extrapolation technique from how to convert the skin friction part which we measure on the model should be extrapolated onto the actual prototype scale. Now there are approximations, they don't always exactly work the same way. So you may see some amount of difference, and these are what are called as scale effects. Okay, now typically this so-called form factor.
Sir,
Yes.
yeah, so what is the difference between this radiation damping and wave making resistance?
Correct. So radiation damping is when I am generating with respect to a oscillatory behavior of the motion of ship. Okay, so let's say my ship is moving up and down in heave. It will generate a wave motion, waves which will be propagating outward.
Okay.
Right? Here I am talking about when I'm moving forward speed, simply just moving forward speed. Still there will be these waves which are getting generated.
Yeah. Yes.
Right? Even though I'm not seeing any oscillatory motion of the vessel.
Okay.
Right? So those parts are called as the wave making resistance. So they kind of really contribute to the resistance of the ship in the sense that they're acting you to slow you down in the surge direction.
Yeah.
But when I'm talking about radiation damping, that will be there in all the modes.
So the major difference is the frequency with which we are operating.
Correct. In some sense, you can think of it like that.
Okay.
Okay. Although it's not technically true, you kind of the boundary between them blurs out a little bit. You can actually see that a portion of this mathematics actually combines with that portion of the mathematics as well, especially when I'm looking at zero frequency. Because when I'm talking about zero frequency, I'm really moving the ship very, very slowly.
Yes.
Right? So what are the radiation damping observed in that time is what I'm talking about. And typically, as long as my ship doesn't have a forward speed, those values should be typically be zero.
Yes.
But here, this is slightly different in the sense that we are talking about that so-called Kelvin wave pattern which we see behind a ship. That also is taking energy to generate. And what is the component of the friction or the so-called damping, which is accounted for that wave making resistance.
Okay.
Okay. All right. All right. So the next part is this form factor for typical ships is about close to 0.1 when the ship is in transit. But if you're looking at dynamic positioning operations, which is at a much lower speed, this form factor kind of comes down to be about 0.25 or so. The idea here is that this formula which we are looking at, the skin friction formula, that is coming from a friction coefficient over a flat plate. So I'm looking at a flat plate and a flow over a flat plate. What is the friction coming in? But the idea is that on a real ship, the ship doesn't have a flat surface, but has a curved surface. So there is some increase in resistance because of the bluntness of the ship, which is not accounted for. That accounting we are doing with the form factor. Okay, all right. Now, yeah, as I said, the residual friction consists of pressure resistance, wave making resistance, also the hull roughness, and wave breaking resistance is also generally included in this so-called residual friction coefficient. Now, if I take this entire thing and I want to express that so-called surge force as a quadratic damping, then I can put some coefficient times u times mod of u. Okay, then that so-called coefficient simply becomes minus half rho s 1 plus k times the frictional coefficient. Is that making sense here? I'm just kind of saying that if I wanted to model this into my system dynamics as a nonlinear damping in surge, right? That so-called nonlinear damping matrix which we had. We had the damping matrix plus the nonlinear damping matrix, which was depending on the relative velocity, right? So if I wanted to include that into here, then the first term of that matrix would be something like maybe C. And that value is given by this expression, given the fact that I know what the skin friction coefficient is, what that form factor are, what is the surface area, and the density of the water. If I know these things, I can approximately compute what this value of this so-called coefficient in damping, quadratic damping in surge will look like. Everybody with me so far? Yes? All right. Okay, now let's talk about the low speed calibration. So whatever we saw here, this formula, which we were talking about, the frictional resistance in the surge damping, this is primarily applicable for slightly higher speeds. But when we talk about dynamic positioning applications where the speed is much lower, we are kind of really interested in station keeping problem, then we will see that this coefficient is not truly representative of the friction. The friction is actually more than what is predicted from this value for sure, for smaller speeds of the ship. So we need some modification for this when we are dealing with low speed vessels. And let's talk about that, what is happening there. So for low speed, the IPTC formula gives too little a damping compared to what we actually observe from experiments. So here, what we want to do is, we want to rather talk about that experienced surge force in terms of what we call as a current coefficient, right? Typically in a dynamic positioning operation, our ship is moving very slowly. So relative to the water, what is the current speed or the water speed relative to the water, relative to the ship? That is what will determine what is the force coming onto it. So we can express it in a similar form as before. Only difference is that instead of this wetted surface area, we now have the projected frontal area. So we know that when we are dealing with the currents, the typical drag coefficient or the lift coefficient are defined with respect to the frontal area rather than the surface area of the vessel, right? Because when we are talking about naval architecture and discussing about resistance of a ship, that's where we were using surface area as the metric. But when we are talking about current forces, we are using the typical norm is to use the so-called frontal area of the ship. Is everybody with me so far? Yes, no?
The frontal projected area means width of the ship, right, sir?
So if frontal projected area means if I take the underwater surface area of the ship and project it onto the front plane. So if I'm standing in front, what is the area that I see? That is the projected area. Okay. Based on that area, I compute generally my current coefficients. for low speed. That's just the method in which we compute them. Okay, and generally what happens is, what you do is, these forces are generally computed in a wind tunnel, which means that we take a very small scale model of the ship, chop it off at the water line, okay, take that model, put it on a wind tunnel, and let the wind go past it. Okay, and when the wind goes past it, we are kind of holding the model and measuring what is the force coming onto the model. Once I get that force, I can typically compute what is the value of rho I know, what is the value of frontal area I know, what is the current speed I know. So I can find out the so-called current coefficient. That is how generally the experiment is performed. Everybody with me so far? And that is what we use for our low speed applications. You generally find that this resistance that you calculated using the previous formula is not very much applicable when we are looking at slow speeds. And that is why we have to resort to experiments to compute this so-called current coefficient. All right. So generally, if you compare the two, you will see that they are different by this ratio of areas. Everybody with me? One coefficient to the other coefficient. One is a skin friction, or the so-called skin friction coefficient, versus the other is called as the current coefficient. The difference between them is that so-called ratio between the areas. Okay, now here also we are mostly interested at low speed areas. So therefore we look at where the relative velocity is close to zero, and you will find that this expression is more or less valid. Now, if I look at the curve as to what is happening with the ITTC line versus the actual one, you'll see that this is how it looks. So here I'm plotting the so-called skin friction computed versus the speed at which the current is coming. So what do I observe? At larger speeds, both the actual one and the ITTC line, they agree well. But when I'm talking at lower speeds, the ITTC is under predicting the friction coefficient. Okay. So therefore, I need a modification for it. I can calculate the current coefficient using the wind tunnel experiments and try to modify the formula by saying that I am applying a different scaling value. So what I will do, I'll do a so-called blending, which means I take this value when UR is high, but I want it to be representing this value when the UR is low. Is that making sense? So which means this so-called sigma function, which I see here, this should be zero when for low speeds or high speeds.
Higher speeds.
At higher speeds, it should be zero, right? So it represents the skin friction formula. At lower speeds, it should be kind of closer to 1, so that it represents the current formula. Everybody with me? Yes? Shadab?
Yes.
With me?
Yes, sir.
All right. So a typical blending function which we choose is an exponential function, which is 1 at UR equal to 0 and decreases to 0 as UR increases. So that's a typical blending function which we may choose in order to figure out how the new friction line looks like. Okay, so that talks about how we talked about the damping with respect to the surge mode. If I wanted to model the surge mode damping, we have these methods to model the surge mode damping. Let's talk about what happens in the sway and the yaw. Okay, in the sway and the yaw, we apply something called as the cross flow drag principle. So what this means is that this is really applicable where the direction of the current and my heading angle are very much different from each other, which means my ship is oriented some way and the wind is coming at a very high angle. Okay, only then I expect to see some sway and yaw forces come in, right? If the wind is coming head on and I'm also oriented into the head direction, I don't expect to see any yaw or any sway. Don't expect to see it. So in that case, when our angle is high, that is when we will be trying to figure out what is that so-called sway and the yaw moments coming about due to this. And they can be computed as, in a similar manner, 1/2 times rho times T of x, where T here is the local draft. Local draft of a 2D section. CD is the drag coefficient at that particular section, times the relative velocity at that particular section, which will be given by the sway velocity plus x times the rotational velocity r. Is that making sense? It's the same formula essentially, but now applied in the lateral direction. I'm looking at what are the forces and the velocities along the lateral direction of the ship. Is everybody with me on this?
So this local draft is at a particular instant of time. What is the amount of draft?
Correct. So you can think, since here we are not talking about waves, we are only talking about current. So what it means is that suppose my ship is not floating at an even keel, but as a trim, right? Then there is a draft which is changing over the length of the ship.
Yes.
Right? So that is the draft it is talking about. Say suppose the ship is floating at an even keel, then the draft will be constant over the length of the ship.
Yes.
Okay, what I'm basically doing is I'm chopping up the vessel into multiple strips along the length of the vessel and saying that each individual strip has a corresponding drag coefficient to it, which I'm trying to find out using current approximations, and then using that value to get my total sway and the yaw moments. You'll actually see that the yaw formula is exactly the same. Only thing is here I multiply by the distance x to convert it into a moment, except that there is no other difference. Okay, so as long as I can find a potential way to calculate this so-called drag coefficient, 2D drag coefficient, I'll be in a good position to compute this y and n. And then similarly, I can, as I did with the surge, I can convert that into a damping value of y VV or YVR, YRV and YRR. I can find out these individual coefficients once I find this y, depending on what is the dependence on V square, what is the dependence on V times R, what is the dependence on mod of R times V, and what is the dependence on R square. Everybody with me so far? So in case that if I wanted to compute, if I wanted to model the damping, I didn't know anything about the ship and I just knew some rough order of magnitude, I wanted to get an estimate of how much is the damping in the ship. These are the methods which help us get there. Okay, so we're kind of drawing from the physics principles and trying to get an answer for it. Okay, these are the methodologies. So typically, if you want to estimate them, this will definitely need some experimental component where we perform those experiments, get those drag coefficients out or those current coefficients out, and then modify them accordingly for our need and calculate the damping values. Okay, everybody with me so far? All right. Okay, if there are different ways to get these drag coefficients, and we are not going to spend too much time on it, and people have done several studies and they have really looked at it in detail by looking at different hull forms, how do these drag coefficients change when the hull form changes. So for a container ship, how does it look like? Or let's say a tanker, how does it look like? So on and so forth. But there are also been other studies where they have tried to kind of make a generalization as to, can I find a single curve which can give me what these drag coefficients look like? And we can use them with a pinch of salt. Okay, sometimes they work well for our ships. Sometimes when our ships are way away from what they regressed on, it may not work as well. Right? They might have chosen 100 ships, and if our ship is not falling closer to any of those 100 ships, this formula may not be applicable. But if it is falling within that, we may be able to use this formula to get a first estimate of our drag coefficients. All right. So as I said, finally, we can again do the same thing as we did with the surge. We can express that force as some nonlinear damping coefficients times these quadratic terms, and then accordingly evaluate what these coefficients are. Once we get these coefficients, we can put these into our nonlinear damping matrix. Okay, that is where they'll find a place. So putting all of this together, we will now take a look at what is the so-called nonlinear equations of motion for our vessel in a 3 degree of freedom system. So here we have our generalized coordinate is x, y, and psi. Body fixed velocities are u, v, and r. And we know that they relate by this rotation matrix, which depends on psi. Coming to the dynamics, we know that we have the rigid body mass matrix, rigid body Coriolis matrix, added mass matrix, added mass Coriolis terms, linear damping and nonlinear damping, and all of that will be equal to the external force that is applied. Now I can combine that all into a neat little form here, where I combine both these mass and added mass to represent by so-called new mass matrix, and all other terms I combine into what is called as a so-called N matrix, which depends on the velocity. So it has both linear and nonlinear components included together. And that is equal to tau, tau n, and tau f. We saw the expressions for all of them, but just to summarize, we have the rotation matrix as here, the mass matrix as seen here, the Coriolis matrix due to the rigid body dynamics. Notice that this fellow does not depend on linear velocity. No dependence on u or v. Okay, we saw that idea, right? We can express the Coriolis term in such a way that it doesn't depend on the rigid body linear velocity. Then we have the added mass matrix, the added mass Coriolis matrix, and again these approximations at zero frequency are working well, decently. Linear damping matrix and the so-called nonlinear damping matrix, just on the basis of what we just derived. That is how we will get the total picture. Is everybody with me so far? Yes? Please tell me yes, no.
Yes, sir.
Yes, sir.
Yes? Okay. All right. Excellent. Okay. So when we do have ocean currents, you remember that I told you that this so-called rigid matrix, Coriolis matrix, we can express it in a term where it doesn't depend on the linear velocity. That is useful for us to deal with currents. We'll briefly take a discussion about it now, but when we talk really about the ocean current forces, we'll discuss that in detail at that time. But let's say our actual velocity of the current is Vc, capital Vc, and it is at an incident at an angle of beta Vc. Then the x component of that will be given by cosine of this angle difference, and the y component will be given by sine of this angle. Can anyone tell me what are these, which frame is this expressed in? Is it in B frame or N frame? Can you recollect this? We spoke about it a while back. I'm just trying to see how much we remember. Even if you don't remember, by looking at the formula, you should be able to make an educated guess.
N.
It's in the n frame. Why?
Like beta and psi we express like all those from the diagram we saw.
It'll be taken as those angles between the x-axis of the NED frame, right? But what is the difference between those angles which I am using?
Oh, that was that high. What was that letter?
No, forget about the letter. Don't bother about the letter. Just see, understand that when I'm taking a difference between the actual direction of the current and my current heading, okay? So that is telling relative to my ship's bow, where is the velocity pointing, isn't it? Then what am I doing? I'm taking its components with respect to that angle. So one along this and one along this. So about which frame would that be in?
B.
It will be about the B frame. Makes sense, right? I'm taking the velocity of the current with respect to the ship's longitudinal direction and then resolving it into components along the longitudinal direction and the transverse direction. So they are about the B frame. Okay, as long as we are not having much heave and roll and pitch going on, they're about the B frame. Sharab, go drink some water and come back. All right. Now, since they are in the B frame, okay, they're not in the N frame. So it's not in the N frame. So when I take a derivative of these, what do I get? I'm taking a derivative of these, so I'll get R times VC times sine of this and minus R times VC times cos of this, which means I can write this derivative of UC as R times VC and V dot C I can write as minus R times UC. Okay. When we now look at the generalized kinematics which we had before, eta dot is equal to rotation matrix times V. Now I'm writing simply that generalized vector V as VR plus VC. Is this making sense? I'm just trying to write everything in terms of a single velocity vector. In this case, I'm trying to write it in terms of the relative velocity vector. Everybody with me on this so far?
Yes, sir.
Yes. All right, excellent. Now the next step is to look at the dynamic equations and also express them in terms of VR. So let's see what's happening there. We are simply taking our right hand side, subtracting these terms, Coriolis terms, damping terms, nonlinear damping terms, and then taking inverse with the mass matrix, we should get VR dot. Everybody with me so far on this? All right. So now this is a so-called state space formulation for us. So we can now write this and express them in a MATLAB ODE 45 and actually can solve them, right? Suppose I gave you all the parameters of these matrices now. So let's say for our KCS ship, I gave you what is the Coriolis matrix, what is the damping matrix, what is the nonlinear damping matrix, and I tell you what is the forcing due to the wind, wave, and I give you what are the control inputs, and I ask you to simulate this system forward, then you can use this set of system to solve it using MATLAB ODE 45. Everybody is comfortable in understanding how that will work? Because this conforms to the form which MATLAB ODE 45 wants you, right? They want you to express x dot as some function of x comma t. So what am I doing here? I am putting eta dot here, vr dot here, and I am giving it as some function of t comma eta and vr. And that function is nothing but this entire thing. Okay, so in essence, this state space formulation is very useful for us, either to simulate the system or to later on discuss about control. Okay? If I ever wanted to do control on the system, to do a state feedback control or a full state feedback or even a measurement based control, this sort of a form in which where I'm expressing it in a state space form will be very useful. Alternatively, so here I wrote it in terms of eta and Vr. I can also write it equivalently in terms of eta and absolute velocity V. If I do that, it will be only slightly different. Eta dot will be R times V. So there will be no current coming into the picture here. We are really looking at the absolute velocities. But in the second equation, now that current thing will come into the picture. Okay. Previously we had Vr dot. So here V dot minus this will become Vr dot. Other things remaining the same. It's just an alternative form of writing it. I may either choose Vr to be the state vector or Vr dot or V to be the state vector. Either case, I can express the system in a state space format and can solve them given that I know everything about the system. Okay, that's the main idea of this so-called 3 degree of freedom system. Now, typically, if the surge resistance and cross flow drag models are utilized, then we can kind of bring in this nonlinear part here where we saw those things can be expressed in terms of their original coefficients. We had previously expressed them as x mod u times mod u, but I can actually write out their entire form if I wanted to, but they are equivalent, right? So similarly, this term is equivalent to y mod vv times mod vv plus y mod vr times mod vr plus mod rv times mod rv plus y mod rr times mod rr. Similarly, I can write down the entire thing. So instead of writing this as a nonlinear matrix times Vr, I'm expressing that as a vector where the multiplication has been done. Okay, just an alternative form if I wanted to express it in this form. Notice that for slow speed maneuvering and station keeping, the linear damping does play a significant role, and the nonlinear damping usually is much smaller. So which is why when we are dealing with dynamic positioning, you'll see that many of the models, even in your VRX model, you'll see that they mostly focus more on the linear damping. When you are looking at very high speed maneuvers or much higher speed maneuvers, we actually tend to see that this nonlinear drag dominates more than the linear drag. And in some particular cases, you may even neglect and get away with removing the linear damping altogether from your formulation, especially if you're looking at higher speeds. Okay, so in which case you may disregard D altogether. Okay, so far the equations of motion wave we have derived, we have looked at the damping which is coming from the so-called first principles approach, which means we are actually modeling the damping using some physical phenomenon, assuming that it is a drag force or it looks like a drag force. So there is some drag coefficient times the square of the velocity times the surface area. That is what we are using in our models to model the damping. But there is an alternative approach which most of you are already familiar with, which is the so-called Abkowitz model, which some of you took. You saw it in your maneuvering course when you took it with me. Okay, or the graduate students must have seen it in the guidance and control of marine vehicles. You must have seen this Abkowitz model come up. So what is happening with that Abkowitz model? So rather than utilizing a first principle approach to modeling the hydrodynamic force, I want to calculate the hydrodynamic force through some coefficients which are obtained by fitting. So which means I am actually doing some experiments, finding out what is the surge force, what is the sway force, and what is the yaw moment which is coming onto the model, and I'm expressing that as a polynomial form. Okay, and I'm playing around with by fitting a curve through that data to identify what those coefficients are looking like. So they don't have a physics basis behind it, but rather have an experimental basis behind them. I hope the difference is clear. Yes? Is that making sense? One is coming from where I'm trying to think from a physics principles point of view. The other is where I'm thinking from, let me conduct some experiments, get the data, do a curve fit exercise, and then get those coefficients out. Okay, so here what we are doing is that we are taking this so-called hydrodynamic force in surge, sway, and yaw, and expressing it as a Taylor series expansion about some nominal equilibrium point. And I'm expressing that as a Taylor series up to the third order, which means I'm considering all the possible combinations up to the third order. And there is a mistake here. Can you spot the mistake in this page? What did I miss? It's a Taylor series expansion. What am I missing? Does it look correct? Don't you think there should be a fraction in front there somewhere? Yes?
Yes, sir.
Yeah. So that was what I was missing there. All right. So that factor is missing, but as long as I can express it as a Taylor series expansion, I can try to understand what these different coefficients which I'm getting them through curve fitting exercise. I'm not actually trying to do a physics-based understanding of how they are coming, but rather a curve fitting exercise is what I'm looking at. So in which case, you will see that the actual number of terms will be huge, because you see I have here 7 different things on which it can depend: U, V, R, U dot, V dot, R dot, and delta. And I'm taking a Taylor expansion, first order, second order, and third order with respect to all those terms, which means that I'll get 7 terms here, 7 times 7 terms here, 7 times 7 times 7 terms here. So you can see that it's a really unwieldy model with so many parameters, and it's not really practical to use that. So we have to make some simplifying assumptions, and that complexity can be reduced by making those assumptions, which are basically observations from physics, where we can kind of say that, oh, because of the symmetry between a port and a starboard, certain of these coefficients will be zeros. And we can kind of reduce that order of complexity of the model. So what are the assumptions which we are making? We are first making the assumption that a third order is sufficient to describe most of the maneuvers that a ship actually undertakes. Okay. The next assumption which we make is that we are only considering first order acceleration terms, which means we are not starting to take terms like x, u dot, v dot. Such terms we are not considering. Right? We are assuming that we are only keeping the terms up to linear order in terms of the accelerations. Then we are also looking at port starboard symmetry, and that will simplify a certain of these forces. And finally, we are assuming that the coupling between the acceleration and the velocity terms is negligible, which means we will not have terms like y v dot r, y v dot r. Such terms will not be there. Coupling will only exist between the velocities. By making all of those assumptions, we can come up with a simplified model, which is what we have written here. So you'll see some other odd combinations up to the third order between all the three variables after the simplification is done. Now, you may even be able to simplify further on certain of these terms for specific ship types or for specific conditions of operation. Okay, but in the most generic form, I have left it here. You should see that this many number of terms should be more or less sufficient for most maneuvers that you're looking at. Note the convention here that whenever I'm putting a subscript, it indicates a partial derivative. And whenever I'm putting double subscript, it includes this factor of 1/2 or 1/6. Okay, don't miss that factor. That is sometimes can be quite significant. Okay, these typical hydrodynamic coefficients are determined from planar motion mechanism experiments. So what we do is we conduct them in a towing tank. We take the model, tow it at a certain speed, and then move it in sway or in yaw, and then observe what are the forces coming onto the model, and accordingly try to estimate our coefficients by a curve fitting exercise. Okay? So we have looked at two different ways. One is first principles based approach of finding out the hydrodynamic coefficients and hydrodynamic forces. The other approach is where we do an experiment and try to find out from experiments, get the data, do a curve fitting exercise, and then estimate the hydrodynamic forces which are acting on the model. Okay, is everybody with me so far? Okay, so these two models are there on our hand. Depending on need and basis or information that we have, we may choose one over the other. So suppose I have experimental data for some craft, I might prefer to go with an Abkowitz model in that case. Suppose I do not have sufficient experimental data and I have to make some approximate values to be there, then I might choose the first principles approach to get my damping coefficients and put that in place. But basically with this, you should have a set of idea of how can I model my craft dynamics and how can I simulate my craft dynamics with this model. This modeling will also form our basis for tomorrow when we are looking at control or with respect to navigation or with respect to guidance. This will be our basis. Okay. A little bit more tweaks we will look at. Specifically for low speed, can we actually change it a little bit more? That is what we'll look at in the coming lectures. But we are more or less coming close to the modeling side of the things. Any questions so far?
So like in both the like first principles approach and like based on the experiments one, so like both we will actually be like from that the x say one term say x mod u. So that will have that CF part, right? So in the first principles approach, then that CF mean we are doing the scale, we are doing calculating it based on the scale only, or the scale model.
Correct. Either you can calculate it based on the scale model or any available data for similar ship types also you can directly use. So you need not always conduct the experiments. There may be some empirical formulations for those coefficients as well possible, in your first principles approach. So if I don't actually have the experimental data for this particular vessel, I may look if somebody has done a similar experiment for a similar ship type. I can take those values and put them in, and I can still get realistic numbers. But suppose I have somebody else has taken a different ship type and performed PMM test on it. I can't scale those values directly for my ship. They are strongly dependent on the geometry of the vessel. Whereas here, since we are non-dimensionalizing with respect to the half rho SV square, those can be ported more easily. It's much more what you call intuitive to port those drag coefficient values from one ship to the other, rather than porting the actual hydrodynamic coefficients from one ship to the other. Okay, because the hydrodynamic coefficients strongly depend on the geometry of the vessel, but the drag coefficient is a more of a it also depends on the geometry of the vessel, but you can make a grosser approximation on it. So if I really don't have the experimental data for that ship, I may be able to choose the drag coefficient order roughly from a different experiment which might have been performed, or somebody else has studied it in CFD. I can get a drag coefficient and I can use it in that sense. Okay.
Sir,
Yeah.
in the first the physics that we modeled, in that case also there are certain coefficients that are not known to us. So for
Correct. That is what Vallabh was asking. Yes.
okay, so in that case also experiments like may be needed.
Correct. But the point is you may be able to port from experiments done on a different ship.
Yes.
You can at least get an order of magnitude closer to what the real values might look like.
Yes.
But if I don't have the hydrodynamic coefficients from one ship to the other might vary more significantly.
Yes, yes.
Because they're a much stronger, they have a stronger dependence on the geometry of the vessel.
Yeah.
So in that sense, it's not that what you call it, one method is immune to experiments. No, you're right. Both are requiring some amount of data which we may not know. But we may be able to get away with some approximations in one method as compared to the other method we may not be able to get away with.
Yes.
Any other comments, thoughts? No? So let me stop recording in that case.